is professor of statistics at Heriot-Watt University in the United Kingdom. His research is focused on Bayesian modeling, inference, and assessment across the interface of statistics, epidemiology, actuarial mathematics, and life sciences. Ayse Arik is a research fellow at Heriot-Watt University, United Kingdom, and her recent research is focused on stochastic modeling of morbidity and mortality, pension de-risking, and Markov type modeling for cancer mortality and relevant insurance pricing. They will present the results and conclusion of their research on the impact of COVID-19 on cancer risk, and more generally on the evolution of cancer risk, research that has been supported by the SCOR Foundation and in parallel with other institutions. We were not alone in this important project. Professor George Streftaris will first present some uneven empirical outcomes on cancer mortality. His findings concern how cancer rates significantly vary across regions, deprivation, and cancer types, with a focus for that exercise on lung cancer and COVID-like disruptions. Dr. Ayse Arik will further investigate the impact of the COVID-19 on pandemic on breast cancer and breast cancer deaths, where these disruptions have caused delays in cancer diagnosis, and she will extract some interesting conclusions for application to life insurance. Please, Georges, you have the floor. I suggest that immediately after your presentation, we continue with the presentation of Ayse. I suggest also that each presentation lasts around 25 minutes. Of course, it's not very precise, but it's just an idea, which will leave us with 40 minutes for the Q&A. Please don't ask questions during the presentation, except if there is a misunderstanding, a problem of understanding of a graph or something like that, an explanation. And in any case, as for all the webinar we are organizing, we will close this webinar at 4:30 p.m. Please, Georges, the floor is yours.
Okay, many thanks, Philippe. Let me share my screen to start with. I hope you can see my screen now. I will make it full screen as well.
Yes, perfect.
Right, thank you. So I'm very pleased to be here to talk about our recent and a bit earlier work as well on modeling cancer risk and how there are differences, as Philippe introduced just a minute ago, in terms of socioeconomic and regional factors. And I mean, we are here today as part of the project that the SCOR Foundation for Science is supporting. Ayse, who's going to talk to you later, is leading the project, which is on estimating the impact of COVID-19 pandemic on breast cancer. What I'm going to talk about for the first 25 minutes, perhaps half an hour, is some earlier work that actually leads to the work that we're doing with SCOR. And obviously there is some overlap with that as well, with the current project. So the earlier work that I'm going to talk about mostly, well, we have a network of people who have worked with whom we have collaborated on this work, on this project. Part of it has also been co-funded, if you like, as Philippe mentioned earlier, by the Society of Actuaries in the US, on a project on predictive modeling for medical morbidity risk related to insurance. Ayse is a collaborator on this work as well, and we also have Professor Andrew Kearns from Heriot-Watt University, just next door to me, and Professor Dodd from the University of Southampton. So just to motivate what we're going to talk about today, which is cancer rates, let me start with this graph here. And what you can see here is a graph of incidence and mortality rates for all cancers together, all different types of cancer together. And this is over time, over years from 2001 to 2021. So we have the rates on the y-axis, the year on the x-axis, and we have four curves. The top
George,
curves.
apologies for interrupting you, but I can't see your slide at all. It's not moving from the first page.
We see only the first one.
Okay.
The page one we see currently.
Right. I've moved to the second.
No, it's not happening. It's not moving here.
It's not happening? Right.
No.
What we can do, George, don't disturb, we can share on our side, and then you say on which slide you are talking and we change the slide.
Right, okay,
okay.
We can do that.
Okay, Zing, if you can drop the sharing of your slides and it will be replaced by... C'est bon, maintenant on met plein écran. Mets plein écran.
Okay, so the slides are not moving? Still not moving? No? That's interesting. Okay, so is... Right, okay, so Zing, are you going to share? Or? Apologies for that, I don't know what's happening, but it's definitely moving on my screen here. Okay.
You don't see my slide?
I don't, well, I can see it now, the first slide.
Is it okay?
It's not, yeah, it's okay. It's not full screen yet. It is now. Okay.
It is on full screen on my screen. Sorry. Should I get to the slide number 3?
Yes, please.
Yes, I am here.
Thank you. So, right. So I've mentioned all this.
Toi, tu ton partage, surtout.
Okay, so I've mentioned all this. So this is the additional funding we had from other sources. I think we've lost the presentation. Is it just me, or can anyone see the presentation on the screen? No.
No, it is low.
No,
Should I?
not now.
What if can I try again and you tell me if it's moving or not?
Now we see it.
Well, I don't. There you go. Yes, thank you. So if we can move to slide 4, I think I've mentioned all that already. So if we can move to slide 4, thank you. So this is so I was saying that I will try to motivate what we're going to talk about by showing you this graph. So the graph is showing the incidence and mortality rates on the y-axis against the year on the x-axis from 2001 to 2021. You can see 4 curves. We're talking about here rates for all cancer types combined together, and these are just the observed rates. We haven't done, I'm not showing you any modeling yet. And we're also looking at age standardized rates. So we have standardized according to age. They're not, what you're seeing is not age specific. It's a general trend. So the 2 top curves that you can see in the graph are is incidence for all cancers, for men at the top and women. And you can see that this is increasing over time generally. It's flattening up in more recent years. And of course, you can see a steep dip in 2020, and that's the COVID effect. The dashed lines, the broken lines that you can see towards the bottom of the graph, this is the mortality for men and women. And you can see that mortality for all cancer types together is dropping. And this is obviously good news. And I'm afraid this is possibly one of two pieces of good news that I'm going to talk about to give you today. The rest of it is not so good news, I'm afraid. The other thing we can see on this graph is that in general, rates are higher for men as compared to women. Now, if we move to the next slide, then we can see a similar thing, but now for a specific type of cancer, that's lung cancer. And we can see that this is the trends you can see on this graph is an exception to the all cancer types together trend, if you like. What we can see with the light color, the light blue color at the top of the two top curves is incidence and mortality for men. So both incidence and mortality for lung cancer for men is dropping. But then when we look at the darker color for women, you can see that the incidence is actually going up to a point. It drops for COVID, but we'll talk about that later. Whereas mortality drops a little bit, not as fast as for men, but it still drops a little bit. So if we move to the next slide, this is then the general trend that we can see in cancer rates. What we were interested in looking at in this work was regional and socioeconomic differences in cancer rates. When we particularly look at factors such as different regions in England and different deprivation groups, as I'm going to say in a minute, are there any differences there? And I will show you that there are differences. And my first question on your slide is, if there is a gap, there is a gap, how big is that gap? Is that gap getting better or worse with time? And unfortunately, we'll see that it's getting worse, according to the data that we have. And what is the future outlook? What can we say about how these things will change in the future? In order to say to answer these questions, we need some stochastics and statistical modeling, so that we make sure that we account for uncertainty and noise. So on the next slide, let's before I show you just a brief note about the modeling we've done, let's talk about the data that we have. So cancer data, and as I said, this is data in England. And it's data on the incidence and number of deaths. It comes from the Office for National Statistics, excuse me, in years from 2001 up to 2021 in some cases. We have age in the data in groups. So for newborn babies, age less than 1, then for young kids, if you like, 1 to 4 ages, and then groups of 5 years of age, 5 to 9, and so on. And then from 95 onwards. Most of the results I'm going to show you are standardized for age, so they will not be specific to particular to specific age groups. And the standardization we've done is based on the European standard population in 2013, which is the usual standardization in demographic and statistical literature. We also have gender, males, females. We have time, as I said, years from 2001 to 2021 in some cases. And we also have the two main factors that I'm going to talk about today, income deprivation, and we have that either in decile or quintile later on, so either in tenths of the population or fifths of the population, with the first group being always the most deprived, and then 10 or 5 later on will be the least deprived group in the population.
Maybe, George, you could perhaps give a little more information on what is deprivation versus what we are accustomed to look at, that is income and wealth, or sometimes consumption. Please, sorry.
Yes, no, that's a good point. So income deprivation, this has to do with particularly with income of individuals. Actually, this is not by individual, it's by small areas. So the whole population is divided in small areas in England, and then for each small area we have an index about which is calculated based on the income of the residents in that small area. So based on that, then we rank the different groups from groups which are most deprived, and that's group 1, down to the group which is least deprived, number 10, group 10. The important thing here is that this ranking and this index is based on income alone. There's a more general index, which is the index of multiple deprivation, which includes other things like unemployment, access to health, other factors as well, which we don't use here. We only use the income deprivation, and there are various reasons for that. One is that it started by mistake. We thought that we had the income, the multiple index, which is based on all the other things, but it turned out that we only had information on income, which turned out at the end that it was a good thing for our modeling, because we don't want to have a real any sort of interaction between, for example, health factors in the index and health outcomes in the data that we're looking at. I'm happy to talk more about that at the end if that's not clear, or if we want to discuss this further. So we also have regions of England. In England, there are 9 main regions. That's the typical classification or split of the English population, the English geography, if you like, from northeast, northwest, down to the south, southeast, and southwest. So 9 different regions. So next slide, we have the modeling. So briefly on the modeling, so there's a lot of work that we've done, and most of our earlier parts of the work are on the modeling for this data. We have what we call here a Bayesian GLM, generalized linear model type model. It's a hierarchical model with different layers. It's a Poisson model for the number of cases, for the number of cancer cases, or the number of deaths from cancer. Mainly what it tells us is we have people moving from a healthy state to a state which is diagnosed with cancer or dead from cancer, unfortunately. And that transition happens with a rate, which we call theta on this slide. And the rate itself, which in my talk will be either incidence rate or death mortality rate later on, it depends on our modeling on a number of factors: age, time, region, deprivation, and gender. Just one equation here. What I'm showing you is what we call the linear predictor in the model. Just one small part of the model, which tells us that the logarithm, actually the expected value of the logarithm of the rate, generally speaking, the rate theta is a linear function of the different factors, the 5 factors, main factors that we are considering here. We have also looked at interactions between those factors, and I'm not going to talk too much about it today. Later on in my talk, I will also add age at diagnosis and smoking as factors, as main factors in this model, but we'll look at that later. And the main, if you like, motivation for doing this, for having a stochastic statistical model here, is because we want to quantify the uncertainty by appropriate credible intervals, probability intervals, as we go along. So next slide, we have the initial findings from this work, and that goes back to a work that was published with Ayse and others back in 2020 and 2021. So before I talk to you and show you more results about differences with respect to region and deprivation, let's see what we found for other factors, for other risk factors. So to start with, we looked at which factors are really important. This is what we call variable selection in statistics. In any case, when we looked at all cancer types together and lifestyle cancers, so cancer types that are supposed to depend on or have the lifestyle of individuals has some impact on them, such as, so for example, lung cancer or bowel cancer. So what we found there is that all the main variables of all the main risk factors that we looked at, age, time, deprivation, gender, and region, they were all important for the modeling, for the model. So they all made a difference in the rates. On the other hand, when you look at types of cancer such as breast or prostate cancer mortality, so the mortality rates for those cancers. And these are not the so-called lifestyle cancers. So these cancers do not distinguish for different lifestyles. So what we found there, perhaps as expected, is that the deprivation factor was not important. And how do these factors change? How do these factors affect the rates? And what I'm showing you here are very general results, which may change from different types of cancer. But in general, we found that age as an important factor. The rates increase with age, so we have higher rates of incidence and mortality at older ages. In terms of time, we've seen in some of the graphs, with exceptions, that we have higher incidence in more recent years, but we have lower mortality. So mortality is going down, and there's a number of reasons for that. Medical advances, better care, better treatment, for example, lead to lower mortality from cancer. In terms of gender, again, a very general result is that men have higher rates than women. And what I'm going to talk for the rest of this of my presentation today is how region and deprivation actually affect those cancer rates. So next slide then is about region and deprivation. What you can see is a map of England, mainly. We have Scotland at the top, but we didn't look at Scotland. Wales is missing. Northern Ireland is missing from the map. So what you can see, the different colors are just the 9 different regions that I mentioned before in England. So we want to look at the regional and socioeconomic differences in cancer rates. So a number of questions that we had from the beginning. Is there a geographical pattern in those rates? And we'll see a graph about that in a few minutes. Are the rates different for the more deprived parts of the population? And the answer will be yes, they are higher for the most deprived parts. Do these differences change with time? They do change with time. They're getting worse, actually. And is the variation, are the differences the same for different types of cancer? No, they're not. Different types of cancer will have different differences, or no differences, perhaps, as we will see in a minute. So on the next slide, then, we are focusing here on this graph on the regional differences, regional variation. And what you can see on the graph is incidence rate. So rates for incidence of cancer, all types of cancer together by year. So incidence rate on the y-axis, year on the x-axis. And you should probably be able to see 9 different curves on the graph with different shades, different colors. Each of these curves represents a different region from the 9 regions that we are considering here. So the first thing perhaps you can see on the graph is that there is an increasing trend for all the regions. All 9 regions have an increasing trend for the incidence rate through time. The other thing that is perhaps not very clear with the color, but I'm telling you that the order in which you can see the different curves on the graph is the same as the order that you can see on the description of the regions on the right-hand side. So starting from northeast, northwest, southwest, and so on. So just if you're not familiar with the geography in England, I can tell you that, well, just by the names of the regions, northeast, northwest. So the northern regions have higher rates, and then southern regions in London have lower rates towards the bottom of the graph. So there's definitely a divide here. There seems to be a divide, as our modeling and data suggest that there's a divide between north and south. And the last point that I want to make about this graph is how the difference between those regions, the difference between the rates and the regions changes through time. If you look at the little oval shape that I have in 1981 on the left-hand side of the graph, you can see the range of the rates for the different regions in 1981. And then if you just jump to 2016-17, the last year in the graph, and you can see that shape, oval shape. On the right-hand side, in the last year of observation, you can see how the range has actually increased. In other words, the differences, the gap between different regions in terms of incidence rates, cancer incidence rates, has actually become wider. And then on the next slide, I'm going to focus on a particular, I'm just taking a snapshot of one type of cancer, lung cancer, and that's incidence again, for females in one particular year, 2017. Map of England again. And now the different shades, the different colors you can see in this map is actually represents different rates. The darker the color, the higher the incidence rate on this map. So you can see dark red up in the north and northeast, that is, and then yellow, lighter color shades in the south. That clearly shows the north-south divide that I mentioned earlier for lung cancer for women in this particular year, but that is a consistent pattern throughout time. The other thing we did here, we were able to quantify exactly how different those rates are in different regions as compared to the average over the entire of England, the whole of the country. And you can see the northeast, the arrow at the top of the graph northeast, we have a 35% higher rate than average, so 35% excess rate. Whereas if you look at the left-hand side, left bottom of the graph, 28% lower rate than average in southwest. SW for southwest. London is at about the middle in terms of the very close to the average for the entire country. Now, if we move forward to looking at a different type of cancer, and that will be breast cancer on the next slide. So breast cancer now, incidence rates again, the same year. Again, different colors, different shades represent different rates. But you can see now the differences, the difference of the color, if you like, the variation of the color is much smaller than compared to the previous graph. And that tells you that the differences in breast cancer throughout across different regions in England are smaller as compared to the differences in incidence rates for lung cancer. The other thing you can see perhaps compared to the previous graph is that although the differences are smaller, the whole map is actually darker than the map that we had earlier for lung cancer. And that shows you that breast cancer actually has higher incidence rates compared to lung cancer. That makes sense. It is well documented that breast cancer is the most prevalent cancer for women in most countries, in many developed countries. On the next slide then, now, I want to now talk about and focus on deprivation differences. Now we have 9 different plots on this graph. To start with, I'm now looking again at lung cancer incidence for females through time, 2001 to 2017. So 9 plots, each plot represents a different region out of the 9 regions. We have incidence rate on the y-axis and on the x-axis time from 2001 to 2017. And on each plot, if you take one plot alone, on each plot, we have 10 different curves. Each curve represents one deprivation group, starting from deprivation 1 at the top, which is the most deprived, down to deprivation 10, deprivation group 10, which is the least deprived. So a few things if we just focus on one graph to start with, one plot, maybe the one on the right top, where I have the arrows, that's York and Hampshire in the north of England. The order in which the 10 curves appear is always the same, from the most deprived to the least deprived. So most deprived parts of the population have higher incidence rates for lung cancer. The differences are getting bigger with time. Again, if you look at year 2001, how the differences look, how the range between different deprivation groups looks like. And then if you look at the same range at the end of the right-hand side of each graph in 2017, you will see that that gap is actually increasing with time. So that's obviously definitely not good news, that the difference in cancer rates for different deprivation groups is increasing by time. The other perhaps important thing with this graph is that the differences, the inequalities, my third point in the legend, is more evident in northern regions. The top line in these 9 graphs represents the north of England, whereas the bottom line represents south of England. And you can see that the rates are higher in the north. The differences are also bigger. For example, London in the bottom left of your graph has the smallest gap, if you like, for different deprivation groups. That perhaps can be explained by the demographics in London having a more heterogeneous population compared to other regions. Now on the next slide, I'm now moving to mortality. So most of what I showed you until now was incidence rates. Now I'm going to talk about mortality, and more particularly, I'm going to talk about projection of mortality. So we're going to look how our model projects mortality to change with respect to, well, deprivation in region in future years. For that, we've used Bayesian forecasting and Bayesian model. It's the same model as before, but we have added a few things, and the things that we've added are shaded blue on this slide. We have added AAD, that's the age at diagnosis. So now we're looking at how theta here, the rate that we're looking at is the rate of the mortality rate, the rate of death. And we have reasons to believe, and it is well documented, that mortality from cancer depends on the age at which cancer was diagnosed. So we use AAD as a factor in this model. And the values of AAD were actually estimated using the model that I presented to you earlier, the incidence model. And we also use non-smoking, NS for non-smoking. It's non-smoking prevalence and a number of years. And we have limited data on that because we want that by year and age. So we fitted the model to fill in the data that we didn't have, if you like. But also we're using a 20-year lag for that, meaning that if we have the non-smoking prevalence or the smoking prevalence, if you like, at a given year, we believe that this will affect mortality 20 years later. And the 20 comes from the literature. I think it's reasonable to assume that it will affect mortality in a number of years later. But how long that lag will be, well, we have relied on the literature to decide a 20-year lag for that. And in order to project into the future, we have used what I call here the random walk. It's a time series model. We're assuming that the time parameter depends on the previous time, the parameter of the value of the previous year, plus some error as we go through time to build up this forecasting model. So on the next slide, we have the results from that. And this is projected mortality now for lung cancer up to 2036. We're looking at lung cancer, as I said, for women. And now this is not age standardized. The first row, the top row, you can see is for age 72 for 3 different regions, Northeast, London, and Southeast. And the bottom line is for age 77. Again, this is a graph of mortality rates on the y-axis by time, on the x-axis. And the 3 different curves that you can see on each graph are 3 deprivation fifths of the population, quintiles of the population now. Deprivation 1, the most deprived, deprivation 3, and deprivation 5, the least deprived fifth of the population. Right, so two things that I have here noted on these graphs is that the mortality for women is not always decreasing, and this is in contrast to what is happening with men. I haven't shown you what is happening with men, but mortality for lung cancer for men. Actually, I showed you the first graph, very first graph. Mortality is always dropping for men, but not for women, not in all different regions, not for all different ages. But the important thing in terms of projection into the future, if you look at on each graph, the broken line, the dashed line with the shaded gray fan around it, that's the projection to the future with a 95% credible interval around it. And if we look at what's happening with the red curve, which is the most deprived, and then the blue curve, which is the least deprived. These never meet. These two curves never meet. Even after 20 years from when we stopped the model in 2018. So even in 2036, if we don't change anything else in what is happening around us, our modeling suggests that the most deprived part of the population will have significantly higher mortality than the least deprived part of the population. And that's a very, very important message here. So on the next slide then, so what I want now to do is to show you exactly how this relative mortality rate between the most deprived and least deprived parts of the population changes by time, and also how it's different in different regions of the population. So again, I'm looking at lung cancer mortality for women up to 2036. And we have defined here the relative rate as the mortality for the most deprived part of the population divided by the mortality in the least deprived. So obviously a value greater than 1 shows that the mortality for the most deprived part of the population is higher than that of the least deprived, which we have already seen on the previous graph. But now on the graph, we have the relative rate on the y-axis, year on the x-axis, and I have plotted actually all 9 regions, but let's concentrate on the blue ones, northwest at the top, southeast, and London. So the broken line shows you the projection to the future. If we just look at northwest, which has the highest relative rate. So northwest in 2001, you can see the numbers at the bottom of the graph. So in 2001, the rate for the most deprived was 2 times 6 times the rate for the least deprived in England. And then if we move at the middle of the graph, in 2018, that relative rate increased to 3.4 times. And if we project into the future, 2036, that will become 3.7 times. So the gap between the rates for most and least deprived parts of the population is increasing based on our data and modeling. Right, next slide then, and I realize that I'm taking up a bit more of the time that I should use, but I'll just mention a few more times when it comes to looking at the impact of delays, diagnosis delays on mortality, and this will bring us, I think, to the topic that Ayse was going to talk about later, which is the impact of COVID-19 on breast cancer mortality. So what we want to see here is how the age of diagnosis, so a delay in the age of diagnosis actually changes the mortality, has an impact on mortality. And it is, well, the link with COVID here is that it is well documented, as you can see on the left-hand side on my screen. That's from the BBC website. At the start of the epidemic, for example, in Scotland, there were about 40% less, fewer diagnoses as in previous years compared to previous years for cancer. So the rate of diagnosis, the number of diagnoses fell because of lockdowns, restrictions, and so on caused by COVID. So what we want to do is to, with our model, to see how this has an impact on mortality. And we do that by going back now to the AAD concept, age of diagnosis. So the equation that you can see in blue there, AAD, so we have added that as a factor that affects mortality. The question, what we want to do here, as you will see on my next slide, is that we want to look at scenarios and see how, if AAD, if the age at diagnosis increases by, let's say, 1, 3, or 6 months, how would that affect cancer mortality? And in this illustration, in this presentation, I'm going to talk about lung cancer in women, and in the years between 2001 and 2036. So in order to do that, we need to make certain assumptions. Well, we need to rely on future population estimates because we're going to talk about the future. So we will use Office for National Statistics estimates for population the population in England in different regions in the future. And we are going to assume that the deprivation structure has not changed in the future. We have then fitted our Bayesian forecasting model by assuming two different scenarios, if you like, more than two, but one, the baseline scenario is that there's no change in the age of diagnosis. And then a different scenario would be that there is a 1 month increase in the age of diagnosis, or a 3 month, 6 months increase, and so on. And then we will calculate the difference in the number of deaths, what we call here the excess deaths, in the two scenarios. And this is shown on my next and final slide, I think. So as I said, lung cancer for women between 2036. If we just look at the numbers of the bottom left of the graph to start with, total excess deaths, the numbers 2034. If we assume that there's a 1 month delay in the age of diagnosis, our model shows us that by 2036 we will have 2034 more deaths from lung cancer for women, with credible interval, 95 credible interval that you can see on your graph. If we then assume that the delay in age of diagnosis increases to 6 months, which is not unreasonable based on how long the COVID disruptions lasted, then the number of excess deaths goes up to more than 10,000, with a significant, with the credible interval that you can see on your graph. These numbers of excess deaths are different in different regions as well. Then if you look at the top left graph, so the numbers change by region. The graph I have here is for the 1 month delay. It's similar for 6 months delay. And the number is also different. The number of excess deaths is different by deprivation on the right-hand side. And it differs by age and year, as you can see at the bottom graph as well. So all in all, there's a significant number of excess deaths caused by delays in cancer diagnosis. And this also changes by time. It increases by time, and it differs by region and deprivation and age in the population. So just to finish my talk, I'll just give you the main points, the summary. So we have seen that there are regional and socioeconomic differences for cancer rates, both in terms of incidence and mortality in the UK, in England. These are actually increasing with time. The good news is that this is not happening for all types of cancer. It happens for, if you put all cancers together, this is true, but if you look at certain cancers, this will not be true for every single different type of cancer. When we project into the future, we see that this gap actually persists into the future. Even in 2036, we still see a gap in rates for different deprivation groups. If we also take into account disruptions similar to what happened with COVID, which increased the age of diagnosis, this will also have a significant impact in cancer deaths in the future. And all this leads to my final point 4, actually, which is a more general question. And if we want to be optimistic, what we want to think about is whether or not we can actually make some difference, whether or not we can convince policymakers to make public health interventions at certain deprivation and region groups, if you like, regional groups, so that we can have lower incidence and deaths from cancer. I'll leave it here. I have some references, some reading, if you like, on the next slide, but let's not spend time on that. I'll just pass over to Ayse, who can talk to you more about breast cancer deaths in the future.
Okay, let us, Ayse, the floor is yours. I'll let you share your presentation, and if there is a problem, I just take on for sharing the presentation.
That's perfect. Let me try. Can you hear me? Because I had some problems here, so I'm not sure. Okay, you hear me. Perfect. So let me try sharing. Oops. So can you see my screen?
Of course.
Okay, then if it is moving, that will be the next question, but now it is stuck. Give me a second.
It does not move.
It will move, but it's very slow for some reasons.
I don't see anything. I am always on the first slide.
Okay, no. Give me another chance to share because I
Yeah,
can...
yes, of course, of course.
Just a second. Let me just quit this and then start from the beginning. Okay, there you go. Let's see if I can get lucky this time. Okay. So is it moving now?
Yeah.
Okay,
yeah, it's fine.
That's great. So everyone, welcome again. Good afternoon, and thanks for still staying and joining us today all together. So I'll be talking about breast cancer risk today, and the focus will be on understanding the impact of COVID-19 related health disruptions. So this is a collaborated work with 5 other colleagues. So George already showed some of them, and I believe 2 of them are among us. Apart from George, Adam must be here too. So this project is funded by SCOR Foundation for Science, but along the way, additional funding also became available from Society of Actuaries. So let me first tie this presentation to the earlier presentation with the aim of explaining why we kept working on cancer risk. Well, obviously, cancer is a major public health concern, but apart from this, it's the leading cause of morbidity and mortality, impacting millions of people every year. And let me give you a striking example here from the UK. According to National Health System in the UK, 1 out of 2 people are expected to experience or develop some form of cancer during their lifetimes. And this means basically, even if we just ignore financial, personal, or physical challenges on individual level, then we still face with an enormous economic burden on a government level that cannot be avoided. The good news is obviously a considerable progress in understanding this disease has been already achieved, all thanks to advanced medical technology and along with vast data analysis and literature accumulated over the years. And this means from insurance companies' perspective, basically the area we are in is changing, and to adapt to these changes, life insurance companies also started focusing on more inclusive insurance products, and SCOR is actually one of them. And in this context, people who are considered not to be insurable beforehand are started to be insured to some extent. This includes women with breast cancer history too. So hereby then our particular focus is going on towards breast cancer risk as part of this particular project. And this is also because breast cancer is the most common cancer diagnosed in women, and it is still one of the leading causes of deaths among women. And apart from this too, from the industry's perspective, this is one of the most common conditions among critical illness insurance claims. So another striking figure here is coming from Aviva. So according to Aviva in 2014, 44% of female critical illness insurance claims in 2014 actually came from breast cancer disease in the UK. So hereby, all in all, breast cancer is actually an interesting topic from research aspect. And what we have done here as part of this project is to look into 2 related research questions. So one question is to investigate breast cancer incidence and mortality rates in the presence of major disruptions to health services due to a pandemic such as COVID-19 pandemic. which cause delays in cancer diagnosis, and also it causes some health and cancer treatments and so on. The second related research question here happened to be to examine related insurance products, life insurance products and critical illness insurance type products by applying the models developed as part of this research project. And we also looked into certain examples in the context of life insurance by making comparisons between our models and the models used by the insurance industry. Well, now this second part of this research topic, there is this project is basically left to another talk because we only have enough time to discuss the half of the project where I'll be focusing on the impact of COVID-19 pandemic disruptions on breast cancer mortality. So let me just first explain what we already know about breast cancer risk. George already mentioned a few very interesting things, and I'm being really lucky because he also explained the available data. What I'll be referring in this slide and the next slide will be based on the population data of England described by George as well. But just to recap, this data is stratified by 9 regions of England and 10 deprivation deciles in each region, apart from the usual variables, age, year, and gender. What we are looking at here is 8 standardized fitted breast cancer incidence in 9 regions of England in 2017 in particular. So the results I'm showing you now is based on the best fitted models applied in the Bayesian hierarchical models, again explained in the previous presentation. So if you look at this graphs, this is a bit different than the graphs you already looked at. The idea here is to highlight socioeconomic and regional differences. So for this, we are basically presenting 8 standardized fitted rates in the most and least deprived deciles in 9 regions of England. And you see an equality line here. And this equality line is to emphasize the fact that if the incidence rates in a given region were equal to each other, then we would expect them to appear on the equality line. But we see these rates in all regions are above the equality line, highlighting the fact that incidences in the least deprived deciles actually higher than the most deprived deciles in the very same region. Also, we see some regional differences here where we observe higher incidences happen to be in the southern regions of England compared to the northern regions of England. Now, in practical terms, this means a woman living in the least deprived neighborhoods of a given region, or having a higher income, if you like, in a given region, or a woman living in the southern regions of England could be at a higher risk to develop breast cancer incidence as compared to a woman living in the most deprived decile or neighborhoods in the same region or in the northern regions of England. So, of course, these differences, as George also highlighted, are less relevant as compared to a lifestyle cancer, such as lung cancer, indicating less controllable risk factors too. Now, if I move to the next slide, now you see 8 standardized breast cancer mortality rates in England again, but this graph is based on a more recent year, which is 2019. So again, this is coming from the modeling results, but different than the previous graph. Now we don't have deprivation as a separate dimension here because deprivation is not found to be significant to explain breast cancer mortality. So what we see is the map of England, and we just put the rates, and I'm hoping you are familiar to this graph because of the previous presentation. What we see is the rates represented in different regions where we see higher mortality rates in the southern regions of England in a similar manner with breast cancer morbidity. And these rates are represented by darker shades of purple. Now, if I just summarize what we learned by studying all this data from an actuarial point of view, now we observe that socioeconomic differences matter to breast cancer morbidity. However, they don't really matter when it comes to breast cancer mortality. However, regional inequality exists and being relevant to both breast cancer morbidity and mortality. Both of these differences are actually less relevant or relatively low as compared to lifestyle cancer, as mentioned, and we use lung cancer as an example there. So the reasons of why we have more equality in breast cancer incidence and mortality is considered to be linked to high breast cancer awareness and also the availability of a national cancer screening program in this case. But if we just put this in a bit more context, if you just look at all these results at a higher level, then we see our results generated by all these statistical models are actually aligned with the medical literature, suggesting less controllable or preventable risk factors. And now, why we know as this is the event, but all this are bringing us to the point why early cancer diagnosis could matter the most when it comes to a cancer type such as breast cancer, because early cancer diagnosis is the perhaps one optimal way to give patients to have a higher chance of survival. And we know this is the event interrupted by the COVID-19 pandemic. So now let me show you what happened during the COVID-19 years. And to show what happened in terms of breast cancer risk, I'll be referring to different graphs. And what you see here is the first one representing breast cancer number of referrals from 2012 onwards up until the third quarter of 2021. Now, what we mean with breast cancer number of referrals is the number of people waiting to see a specialist after their first contact with a GP with a suspicion of breast cancer tumor, if you like. And here we have different criteria in Scotland, changing 31 to 62-day waiting periods. And if you look at the graph, we see the number of people waiting to see a specialist. Actually, they are leveled up over the time up until 2020, but these numbers are declining significantly and being as low as 36% as compared to the same period in 2019. So if you look at England in the same context, so they have a different metric to measure this. Now, the number of people waiting to see a specialist within 2 weeks in England actually dropped at a much higher rate, and this fall is as low as 76% as compared to the same period in 2019. So these numbers in Scotland are translated into a fall in breast cancer registrations, and we have a figure there coming from Public Health Scotland suggesting a significant fall by 19% compared to the pre-pandemic period. Now, the second set of figures I would like to show you in the context of what happened during the COVID-19 years is involving breast cancer incidence and breast cancer mortality in England on annual level. So these graphs are changing from 2001 to the most recent calendar year, which is 2020 for breast cancer incidence and 2021 for breast cancer mortality on the right. If you look at the figure on the left here, showing us breast cancer incidence, well, both figures are split by age, and the figure on the left is showing us breast cancer incidence is actually a bigger issue starting from age 50 onwards, as the gap suggested. And we have an increasing trend over the time up until 2019, followed by a significant decline in 2020 because of the health-related disruptions caused by the national lockdowns. And the drops here are as low as 25% at age 60 to 64. Again, compared to the same period in 2019. And in parallel, if you look at what happened to breast cancer mortality by age, we see over the time breast cancer mortality rates are declining. And if you look at what happened after 29, we see in 2020 there are some increases in breast cancer mortality, but this is mainly from age 65 onwards, and they happen to be as high as 7% in that year. So this basically suggesting perhaps in the shorter term, older age groups are impacted at a higher rate or much more quickly. But in terms of mortality in the future years, of course, we expect a kind of delayed impact that could lead to higher death rates in the future. And here, the main purpose, now I can just move on to quantify what we could potentially expect to happen in the near future. So then we, after just studying all this, after looking at all this, if we could take a moment to think about what we know, we understand breast cancer is a cancer type suggesting more equality compared to other cancer types. And it makes sense to focus on perhaps an age-specific model. Now, our challenge here happened to be not having a comprehensive data. And in the absence of a comprehensive data, we focused on a Markov type modeling. So here, what we see is a diagram summarizing the model, and this model is involving 6 different states, where the initial state is considered to be state 0, where women could stay with undetected breast cancer cases or being healthy. Now, what we do here is basically to define the life history of a woman or an individual by considering 2 main events. And the first event we are paying attention is the experience of breast cancer. And the second event here is the death. We are considering 2 different causes of death. One is death from breast cancer, stage 5, and the other one, the second cause, is death from other causes, are stage 4. So apart from these 2 main things, we have done 2 significant things with this modeling. We considered we distinguished between different cancer stages, and we did this by considering stage 4, which is the latest stage of breast cancer, under metastatic diagnosis stage 3, while categorizing the rest of breast cancer stages between stage 1 to 3 under pre-metastatic diagnosis, which is our stage 1. So then one significant improvement in this model compared to earlier models is to distinguish between cancer stages. And the second significant thing we added to the literature is to introduce a state involving undiagnosed or unobserved breast cancer cases. And this is done by introducing stage 2. The reason why we introduced a stage 2 is to quantify the impact of pandemic, because we will find a way to just identify how unobserved number of people, women waiting with breast cancer changed during the pandemic later on. So 2 significant assumptions we made here. Let me just highlight those as well before moving on. So we are assuming death from breast cancer in this model is only happening after developing a metastatic breast cancer, which is the latest stage of breast cancer, following the medical literature. And the second significant assumption here, we are accepting breast cancer treatment or any source of treatment could be available in stage 1 with a diagnosis. However, this wouldn't be the case in stage 2 for a woman with breast cancer, provided she has no diagnosis. So we improved this age-specific model further by introducing duration dependence in certain states. So I refer state 1 and 2, and in these 2 states, we introduced duration dependence along with age dependence. And in this way, we aim to make the overall model to be more realistic, and this is motivated by the medical literature suggesting time spent with a pre-metastatic breast cancer condition could matter to develop a metastatic breast cancer condition. So in this way, by introducing duration dependence into the overall modeling setting, in technical terms, we changed the Markov model into a semi-Markov model. Now, we have one slide involving some equations, and these will be the only equations I will be showing you today, so hope you can just bear with me. So the question after developing this model is, of course, how to calibrate the model, and this basically poses the second biggest challenge for us because of the existence of stage 2. If you look at the diagram, you see stage 2 is showing pre-metastatic unobserved or undiagnosed. So the challenge here is how to measure something not observed. So to do this, we basically focused on 2 simple things. The first thing we focus on is the first equation here, where we define the onset of breast cancer. So the onset of breast cancer is defined following this particular equation that I tried to highlight, but it's not happening. Here we go. So we define the onset of breast cancer considering diagnosed and undiagnosed pre-metastatic cancer cases. And there we introduce a parameter called alpha. And this alpha is showing us percentage of diagnosed breast cancer cases in overall breast cancer cases, either diagnosed or not diagnosed. This gives a way to identify the rates of transition to pre-metastatic unobserved. The second thing we focused on is the assumption we made between stage 1 and 2 linked to the availability of breast cancer treatment. If you look at the last equation here, it basically establishes a relationship between rates of transition from stage 1 to stage 3. What we say here is what we do here is to introduce a second parameter called beta. And with this beta, we somehow proxy to the developing metastatic breast cancer in the absence of treatment. So what we say as the rates of transition from stage 2 to 3, in other words, developing metastatic breast cancer in the absence of treatment would be at a much higher pace compared to the case where treatment could be available. Now, after doing all this, after finding a way to parameterize the model using the population data of England and the medical literature when we don't have the data, we managed to calibrate the overall model and we quantified some results. To validate the results, we looked at breast cancer net survival rates. And for this, we are referring to the definition of the Office for National Statistics. And in this way, we managed to make some comparisons to understand whether or not our results have made sense in terms of empirical evidence. So here, we make the assumption, so we need to make an assumption about alpha and beta parameters. So in this slide and in the following 3 slides, what we are assuming is 60% of all breast cancer cases are assumed to be diagnosed, and we are accepting the rate of developing metastatic breast cancer in the absence of treatment could be 7 times higher as compared to the usual circumstances. So we are also carrying out a sensitivity analysis, but I'll just come to this point. At the minute, just keep in mind that we do the calibration using the available data and medical literature and by relying on this information. So this gives us net breast cancer survival from pre-metastatic breast cancer on the left and metastatic breast cancer on the right, as you see. So we just calculated the survival rates for the insured age groups between 30 to 60 over 10-year period. And if you look at the scale of these two rates, what we see is basically there is a big drop from the survival from a pre-metastatic breast cancer as compared to survival from metastatic breast cancer condition. So we see women, even at age 60, even after a 10-year time period, is still have a very good chance to survive from pre-metastatic breast cancer, which is higher than 95%. However, this rate is this chance of survival is significantly dropping if the underlying condition is a metastatic breast cancer, the same age group. Another significant thing here is, although we see the usual age pattern on the right, if you look at the breast cancer survival on the left from pre-metastatic breast cancer, we observe an unusual age pattern here at different age groups. It is suggesting basically pre-metastatic breast cancer survival at an older age is more likely compared to a woman at a younger age group. So the reason of this unusual age pattern is because of 2 reasons. One is the availability of national screening programs offered to older age groups at an earlier time period, and also the type of the breast cancer developed by women at younger age groups. Apparently, that type of cancer is more lethal and more aggressive, leading to an unusual age pattern as we see. So the good thing about all this, our overall results here are aligned with the medical literature, and importantly, our models are capturing unique age patterns in each case. So this gives us enough confidence to move on and then look at some COVID-related scenarios, if you like. In the paper, we looked at more than one scenarios, but I will be talking about one single scenario here, where we have made two changes as compared to the pre-pandemic calibration. Here, the changes we have done in the pandemic calibration are impacting the death from other causes. We assume an increase there as compared to the pre-pandemic calibration due to COVID-19 related deaths. And also in parallel, we are assuming a decline in breast cancer diagnosis, to be specific, a decline in pre-metastatic breast cancer diagnosis. So this will be impacting the highlighted rates of transition. And as we know, the pandemic has no known impact on accelerating the onset of breast cancer. So this means we would expect the onset of breast cancer would be unchanged before and after the pandemic. So in mathematical terms, this means whenever we assume a slowdown in breast cancer diagnosis, this then must increase the undiagnosed cases. So we have done our calculation for about 5 years, starting from January the 1st, 2020 onwards, and we have made a number of different changes, as you see, summarized in these related rates of transition. The numbers presented in the table are coming from Public Health Scotland and England, rather than making pure assumptions. So when we have done this, we had a chance to calculate a number of different outputs. I will be showing you two different sets of outputs. The first one is about how the breast cancer incidence and mortality rates, for instance, are changing over 5-year periods as a result of these sort of initial health disruptions. So we have done the calibration under both modeling settings, on the semi-Markov and Markov modeling setting. We have summarized results here. If you look at the second bullet point, for instance, here, we see over 5-year period, we expect to observe 3 to 6% decline in different age groups between 65 to 89 from pre-metastatic in the diagnosis of pre-metastatic cancer as compared to the pre-pandemic calibration. So in parallel, we could see a 3 to 5% increase in different age groups between 65 and 89 in metastatic breast cancer cases under Markov model, where we have a slightly bit more optimistic guess under semi-Markov model. So it is possible then using the model to quantify such outputs, but as you see, Markov and semi-Markov models are suggesting differences under certain cases because of the assumption linked to duration dependence. So the good thing about Markov type modeling is it is possible to translate all calculated values into more popular metrics, such as excess deaths or years of life expectancy loss. So what I'm presenting here is excess deaths and years of life expectancy loss from different causes by assuming we would have 100,000 women at all these different age groups between 65 to 89. And this means what we see here is about or related to 500,000 population rather than a real population. And the calculations are made under different modeling assumptions. Let's see one of them. Let's look at one of them. If you look at the one highlighted here, which is about excess deaths from breast cancer under semi-Markov model, this is suggesting 6 to 10 additional or excess deaths over 5-year time at each age group out of 100,000 women at each age group at a time. And this number, 6 to 10 different excess deaths at different age groups, would be associated with 3 to 6% increase in death from breast cancer in the semi-Markov model as compared to the pre-pandemic calibration. It is possible to translate this information into years of life expectancy loss. If you look at the last column here, very last one, this would mean an increase in years of life expectancy loss changing between 35 years and 193 years. So we carried out a sensitivity analysis to account for model uncertainty to some extent. And for this, we mainly looked into 3 different things. And how we have done a sensitivity analysis is basically changing one parameter at a time by keeping all the rest as it is. So we looked into a change in the percentage of diagnosed breast cancer cases associated with this alpha parameter. We also looked at a change in the rate of developing metastatic breast cancer in the absence of treatment that would be associated with beta parameter. Plus, we also looked at a change in the level of breast cancer mortality. Now, we have certain, so we have the associated parameter values, and we are also showing the overall impact. If you look at 1 or 2 of them, let's pick up the first one here, for instance. So you might remember that we assume 60% being equal to alpha in our previous baseline scenarios. So this meant that we assume 60% of diagnosed breast cancer cases. Now, if we think this to be equal to 40% instead, so in an essence, what we think is a kind of worse health system, only capturing 40% of the overall breast cancer cases in diagnosis, if you like. Now, if we imagine a worse health system in a non-pandemic period, then this would mean an increase in breast cancer deaths at different age groups, changing up to 3%. And if we imagine a better health system, perhaps capturing 80% of overall breast cancer cases in the normal times, then for that health system, then pandemic has a kind of more dramatic impact, leading to an increase in breast cancer deaths changing between 9 to 12% at different age groups in the post-pandemic environment. So let me just wrap up all this discussion. So what we have done here is to examine breast cancer risk, and we identified that breast cancer risk has more equality as compared to lifestyle cancers. So in this project, we focused on developing a model, a versatile model, with the aim of having more impact. And if you think about this particular modeling setting, it is just relating to delays in the provision of breast cancer diagnostic and treatment services that could allow us to imagine different health service provision in different countries in non-pandemic times. And also it could be useful to quantify impact of any pandemic in different health services to make comparisons. What we have done here is a calibration using the population data of England and the medical literature, and our calibration is suggesting 3 to 6% increase in deaths from breast cancer between age 65 to 89 over 5-year periods. So we demonstrated the importance of duration dependence or the significance of relating to medical literature while developing this sort of models. What we have done is to basically account for parameter and model uncertainty in the traditional statistical sense, although we carried out an extensive sensitivity analysis. So I would like to finish the talk by also talking about some implications. So this study is not only for actuaries. So we are actually aiming a wider public, for instance, by informing policymakers too. So we hope that these sort of models can become more popular to implement evidence-based health interventions in near future. And I would like to highlight that we are just in the time where we observe all these different amazing medical technologies, and these are allowing to have early cancer diagnosis at faster rate, is changing rapidly. So this means we need to reevaluate what we know about all these different types of risk with the aim of extending the insurance products. And this can lead to more inclusive products by giving more options, more support to people, and this is linked to fairness in insurance pricing as well. So as in the second part of our project, we also, as mentioned, looked into life insurance type products. We just demonstrated how these models could be applicable in the context of life insurance and what the advantages are. We made some comparisons using the industry-based models as well. So this can be found hopefully in the upcoming paper. It's already under review, but I would be happy to share if you are interested in that. We know there are more extreme events are coming up, So with the by accessing more data, hopefully in time we can just further develop this sort of models, and that would be nice. So there are further readings here, and thank you for your patience. Thank you for listening to me. I'm stopping sharing now.